very pleased to introduce Leslie Brooks. So Leslie is currently working for one of the, as a senior consultant for one of the top 3 U.S. defense contractors. And I actually met Leslie, I believe it was about 15 years ago, maybe even further back than that, at an AQAA meeting. Always been very active in the community and given many presentations at AQAA meetings as well. He has always been very involved with automation and leading edge technologies. I know when he started working at GM, he got the opportunity to do a lot of specification by example stuff and trained a bunch of people on that and had wild success with that as well. So really pleased to have Leslie talking to us today on the intersection of specification by example and some of the AI and machine learning topics that we've talked about. So take it away, Leslie.
Okay, let me share my screen. All right. So we're going to talk about specification by example, or as it is more frequently, but I think less accurately known, BDD, or behavior-driven development, and how that applies to data science. So what we're going to talk about, what we're going to cover today is, first of all, why are requirements for data science and machine learning any harder than requirements for a website? How can we apply specification by example to data science and machine learning applications? How do we actually write the requirements? How do we automate the testing and deliver it early? Deliver it to the developers before they finish writing the code? What problems and pitfalls should we be aware of and try to avoid? So first up, why are requirements for data science and machine learning any harder than requirements for other more common applications? Well, traditional applications are completely deterministic. When you write requirements for a website, you can list exact preconditions, exact steps, and an exact expected result. If you're writing requirements for an API, you can do the same thing. Preconditions, steps, expected result, they're all known. There's no ambiguity about it. And if the outcome doesn't match the expected result, then you have a bug. No questions. Data science and machine learning applications are not deterministic. Many parts of data science, machine learning, AI have unpredictable outcomes. Outcomes will be unpredictable when the problem has hundreds or thousands of variables. There isn't an exact solution to the problem. If there were an exact solution that was easy to calculate, we could calculate in finite time, then we wouldn't be turning to data science and machine learning for an answer. We'd just calculate the answer. So since we can't calculate the answer, we have to search for a good solution. And in a search space with hundreds of variables and nonlinear relationships, the good solution that you find very much depends on where you start looking and what algorithm you use. And many search algorithms inherently include randomness. For example, some of them will pick. So with neural networks, we don't understand how the node weights produce the outcomes. We don't understand how we arrive at the weights we do after training. And we don't understand how, if we change a particular node weight by a particular amount, how that's going to change the outcome. So that is even another level of complexity. And if we don't understand it, we certainly can't write traditional requirements about it. So how do we apply specification by example to data science and machine learning? If we can't predict the outcome, how can you write requirements that include an expected result? Well, fortunately, there are large parts of data science and machine learning that are predictable, and we'll talk about those. We can sure write requirements there. All of these applications depend on huge amounts of input data, hundreds, thousands, maybe even tens of thousands of variables, and for those variables, maybe thousands or tens of thousands of different samples, different data points at different points in time, different geographic locations, whatever type of variable it is. All of that data has to go through what they call ETL process, and that is extract, get the data from a source location, transform it, process it, clean it, modify it, scale it, do all manner of adjustments to it, and then load it. Okay, extract, transform, and load. The ETL process is completely predictable. We can definitely write requirements for that. The ETL process cleans and normalizes the data. When we're getting data from hundreds of sources, it's different sources, it's always going to be dirty. Some values will be missing, some will be invalid, some are going to be text rather than numbers. You may have a device number that is uppercase alpha and numeric from one source and lowercase alpha and numeric from a different source. Maybe a different third source has something appended on the end of the device number. You have to clean all of this stuff up before you can feed it into your machine learning application. So things like invalid values get converted to nan, not a number. A single variable that could be reported on more than one scale will be converted to a common scale. So for example, one version of a machine might return temperatures as a binary number between 0 and 256, 8 bits of precision. 256 represents full scale, say 255, sorry, say 1,000 degrees. And a later model of the same machine, they may have upgraded the sensor so that it returns 10 bits rather than only 8. Same scale, same temperature range, but more precision. So now it's 0 to 1,023, and 1,023 represents 1,000 degrees. So the ETL process will convert both of those to a common scale before handing them off to the data science application. Missing values, we'll interpolate probably for missing values. And all of this is deterministic, and we can write requirements easily for all of this. So here's a requirement. Given an 8-bit precision temperature sensor and a reported temperature of 255, when the temperature is normalized, then the temperature will be 1,023, full scale. So we have a requirement, and it specifies exactly how you normalize the data if you're getting it from an 8-bit sensor, but you also have 10-bit sensors for the exact same value. You want them both to be on the same scale. So Next thing, many data science applications have a feature generation step, probably most of them or even all of them, but feature generation is deterministic. What this does, it takes raw input variables and converts them into features, identifiable attributes that the application can then use for classification or prediction. So think of features in data science like landmarks. You use landmarks to tell someone how to get somewhere. If you wanted to find the Skycraft surplus store in Orlando, Florida, I would tell you to drive east on Fairbanks until you see a building on the left with a flying saucer on the roof. The flying saucer is a landmark. In data science terms, a feature. You may have lots of variables, but only a few useful features. Feature generation converts those raw variables into useful features, just as you have many buildings, but not many of them are useful for landmarks. This flying saucer on the roof on the left is a good landmark. There may be others on the right, but the one on the left is a good landmark because it's unique. Another way to think of a feature is in terms of image recognition. If you see a picture of the front of a car, you're asked to identify the brand of the car, you'll probably look for a distinctive logo. So if you see a stylized double R, you will say, that is a Rolls-Royce. And we would call that stylized double R a distinctive feature of Rolls-Royce vehicles. And in image recognition, it would be a feature. So this is a simple example, but features can be very complex. They could have multiple input variables. They could be defined as the slope of a line or the second derivative or other, even more complex functions. For example, you might have a machine that has pressure sensors before and after a coolant pump. And neither pressure sensor strongly predicts a machine overheating event. But if the pump starts failing, then the pressure differential between those two pressure sensors will drop. And that could predict machine overheating. So the pressure difference might be a good predictor or a feature. So we would define the pressure difference, P2 minus P1, as a feature. And we can write requirements for features. Given pressure P1 is 100 and pressure P2 is 150, when feature generation is performed, then PDiff will be 50. So this is all completely deterministic. There's a huge amount of processing that goes on in the feature generation step. And if it isn't done correctly, then the machine learning steps may not work at all, or they may work far less well than they should. So this should be a major focus of your requirements to make certain that your feature generation steps are working correctly. First of all, that they're defined, and then that they are working correctly. So again, this is a trivial example, but it's a critical step in data science and machine learning applications. And writing requirements for feature generation will be very, very valuable. Writing requirements here will also uncover new requirements. Given these sensors and values, there's sensor 1, what's the value? There's sensor 2. When feature generation is performed, what's going to happen? Well, the QA people are certainly going to think about, what if there's no value there? And so then you ask the data scientists, what do you want us to do when we're generating features and there's no value there? And they may say, interpolate between the two values on either side of that, if this is, say, a time-stamped sensor reading. Or they may say, discard it, or convert it to 0, or whatever. And so you write the requirements here, and then you can test against those requirements. We actually had a situation like this once. I was working with the data scientists to write the requirements, and they said, oh, sometimes there's a sensor, but no value is reported. And we discussed how that should be handled. And then that made me think, well, what if the same sensor value appears twice? Same sensor, identical timestamps, but two different values. And that led to a new requirement. And that's one of the powerful advantages of specification by example. I hope that you watched Seb's presentation yesterday on the value of living documentation. But this is one of the values of specification by example as a methodology. Listing concrete examples helps us to discover additional important examples. So as I said, writing requirements here is going over new requirements. So here's our new requirement. Sensor 1 appears twice. Two values, same sensor. When feature generation is performed, in this case, the data scientist said, put them both in the feature. Use both of them. So that's what we wrote. So now let's look a little at another aspect of data science and machine learning. One very, very common use of data science and machine learning and AI applications is to predict something. Will the stock market close up or down today? If you can predict that, you can make money. What is the probability of this machine failing within the next month? Very valuable, depending on the value of the machine, I guess, and the cost of the downtime. When will this machine need maintenance in order to prevent failure? We want to perform maintenance before it fails so that we don't have unplanned downtime, but we don't want to perform maintenance if it's got another 12 months to go and we can easily do the maintenance 11 months from now. Why would we do it today? Predictions depend on features. And we've already seen that we can write requirements for features. We can also write requirements for predictions. Given these features and values, when we forecast the stock market direction, then the forecast will be up. Now, I have to add some caveat here that data science and machine learning models can be simple enough for us to write these types of requirements, but can be does not mean will always be. Models that have hundreds or thousands of features are probably too complex for us to write requirements, or certainly to write all of the requirements that we would need to thoroughly test it. So we may be able to write only a small portion of the total number of possible requirements. We might be able to write requirements for some of the simpler cases where one or two features completely determine the outcome, but we could still be unable to write requirements for really complex cases where hundreds of features jointly impact the outcome. And neural networks are typically too complex for us to be able to write requirements this way. Again, since we don't understand the relationships between node weights and outcomes there, why writing requirements this way is just not going to work for that type of an application. Another thing that's frequently done with data science and machine learning applications is classification, deciding to which of several categories an object belongs. Is this device broken or working? Is this a cat or a dog? In what language is this message written? Is this a human or a bot? Useful to be able to classify. Classification also depends on features. And we can write requirements. Given these features and values, and there they are, when we classify the object, then the classification will be broken. Yeah, this one's dead, we got to replace it. And as with predictions, these models can be simple enough for us to write these types of requirements. Can be does not mean will always in all cases be. Some of them are very, very complex, and if they have dozens or hundreds of variables that are all jointly determining the outcome, you're not going to be able to write something that is understandable that looks like this. I can think of ways to attack that, but it would be very challenging. And again, neural networks are a special case because we don't understand the internal workings. They're going to be typically too complex for us to write this type of requirement for them. And Costa, if you have any questions show up, why, feel free, if you feel they're pertinent to what we're talking about right there and then, go ahead and jump in and raise that question so that we can discuss it right there in context. Should have said that earlier, and I forgot to.
Actually, we just had one. Yeah, we just had one come in. So Charles asks, in the machine learning AI domain, do granular requirements really matter as long as we can validate the results? Or do the constraints of polynomial time make this approach impractical? And he goes on to say, I ask this because the topic seems like a first cousin of P versus NP problem, calculation versus validation.
If it were calculatable in finite time, we wouldn't be turning to data science, as I said earlier. But it is an NP problem. So the requirements, though, are very valuable in that when you get to the NP parts of the problem, you're guaranteed that those are not going to work properly if you have messed up any of the ETL or feature generation steps. So it's very important that we write requirements for those earlier steps in order to know that what we're feeding into the machine learning parts is valid, usable, clean, properly formatted data. I hope that helps. If there's more to that, feel free to raise another question a little later. So what about the non-deterministic parts, the truly NP parts in many cases? Well, some parts are inherently non-deterministic. So how can we write requirements, much less requirements with concrete examples, for things that are non-deterministic? Well, data science applications still have outcomes, and those outcomes can be described. Sometimes the only description is statistical, but that can still help. And we'll see why, and I can share an example from experience. Suppose we have a machine learning system that optimizes pressure, temperature, and acidity in a wine fermentation process. The desired outcome is to minimize bad tasting fermentation byproducts in the wine. So If we know from our chemistry and our fermentation expert that the temperature during fermentation should never exceed 95 degrees, else it's going to generate more bad tasting byproducts, then we can write a requirement about that. If given a fermentation temperature of 90 degrees and the temperature is increasing at a rate of 5 degrees per hour, then the cooling water flow rate will be at least 50 gallons per minute. We can calculate, we're testing a boundary condition, and we don't know the exact flow rate that the machine learning system will select, but we do know we can calculate that the rate must be at least 50 gallons per minute in order to stop the temperature rise and prevent the tank from exceeding 95 degrees. So if the machine learning system selects a lower rate, then we know that we did something wrong either in writing it or in training it. Specification by example says that we must use concrete examples, and at least 50 would not normally be acceptable. In an application that has deterministic outputs, at least 50 would not qualify as concrete. But in a non-deterministic system, we may not be able to specify boundary conditions more accurately. So these are non-deterministic requirements for a non-deterministic system, but they can still add value. I've actually seen a situation where we wrote requirements similar to this, and a very subtle software change caused a requirement like this to fail intermittently, where previously it passed every single time. And that flickering behavior alerted us to the problem, and we eventually tracked it down to the exact line of code that caused that problem. We should always test for the boundary conditions, even in the non-deterministic parts. And we can set our boundary conditions so that we have some value, but we don't have false positives. We don't want false positives because then people don't trust our tests. So if we set a one-sided boundary condition, 3 standard deviations from the mean, we're going to get roughly 1 false positive per 1,000 runs of that test. If you have multiple tests, you have to do your math to verify that your false positive rate is going to be low enough to be acceptable. If you set it 4 standard deviations away, then you're going to get 1 false positive per 30,000 test runs. If you're using double-sided boundary conditions, then obviously your false positives are twice that rate. We normally think of flickering tests as a great evil, something to be avoided at all costs. But when the system we're testing is inherently non-deterministic, we're forced to deal with the non-determinism. And that means we are faced with some difficult choices. We can set the boundary conditions so close to the mean that we get at least 1 failed test on every run. That's not good. No one's going to trust our tests. We could set the boundaries so far from the mean that the tests never fail, even when the software is grossly broken. And that's bad because no one should trust the tests. We could write a requirement about the mean and the standard deviation, and we could run the tests enough times to calculate those from the result. That can add value, but it's going to cost in test run time. And you would never want to put that in your CI/CD pipeline unless those tests are blindingly fast, which I would think would be very unusual. So the most reasonable choice seems to me, this is my opinion, to be to set the boundaries far enough from the mean that we get a very small number, a manageable number of false positives, but close enough to the mean that the test is likely to fail if the software is truly broken. That's not perfect, but not perfect is the definition of data science machine learning software. If there were a perfect solution, a formula that you could calculate in reasonable time, finite time, to determine an exact solution, you would not be turning to data science and machine learning. So, automate the testing and deliver it early. Tests delivered early have far more value than tests delivered late. Ideally, we want to be delivering tests to the developers during the sprint before they have finished the code. Finding bugs during the sprint means a whole lot less time spent debugging. The developer doesn't have to remember what they were doing 2 weeks ago. They have to remember what they were doing a few hours ago. And that greatly narrows down the section of code in which they introduced the bug. Write the requirements collaboratively with the product owner, in this case, probably one of the data scientists, the business analyst, a QA, and a developer. Writing the requirements collaboratively is hugely important. This is the essence of specification by example, or BDD. Seb Rose spoke about this significantly yesterday, that the collaborative aspect is the key aspect of what we're doing here. If you leave out any of these groups, you're going to cause problems for yourself, because you're not going to create the ubiquitous language that is essential for specification by example to add value. The people who got left out aren't going to know what this word means in the context, in the way that you're using it, because they weren't there in any of the meetings where you defined your terminology. Now, Seb said that you can have only one or a couple of these groups write the requirements. And I believe the way he said it was, after you have gotten started and you've gotten your language settled, then anybody should be able to write down the requirement from the user story. But then you need everyone to review those requirements so they all agree, yes, we understand these, and we're ready to develop, to test, to accept, whatever our role is, the software that is developed here. Having all the players, though, present is valuable. It gives you an important diversity of viewpoints. The developers will think of problems that don't occur to the data scientists, and the QAs will see some boundary condition that everybody else missed, and so on. So there is value in having multiple viewpoints on the requirements. Second, automate the requirements in the same language the developers are using. Most data science and machine learning development is done in Python. If that's what the developers are using, then that's the correct language for test automation. In the Python world, the correct specification by example automation tool is behave. So you would use behave. Automating in the language that the developers are using provides some huge advantages. If you have a bug that you can't figure out in the automation code, or you don't know the best test library to use, best library to use, you can ask the developers for help. You can share code back and forth. The developers can say, here, this is the way we call this API. You can read this code to understand what we did, or you can use the code. If you need to understand how their code works, you can read it. This has been valuable to me many times. The developers can help you update the automation code. When the developers start updating the code, your life will become much, much easier. Add the automated tests into your build pipeline. Critically important that you do this. Integrating the tests into the build pipeline means that you must have robust tests. You can't be failing the build for false positives half the time or even every day. So it forces you to write good quality tests, but it also means that people learn to trust them and they see them every single time and they're delivering value. Fail the build if the tests fail. Once the tests are integrated into the build pipeline, if you've written requirements collaboratively and you're using the same programming language as the developers are probably going to start updating and maintaining your code for you. I worked on a project once where we were testing embedded code, and we had to detect what was going on in the system by parsing the log messages that the system generated. The developers were constantly changing the log messages and breaking our tests. Once we got the tests integrated into the build system, changing a log message meant breaking the build. And everyone could see who had checked in the last changes before the build broke. And the developers didn't want their name on that. So they then did one of two things. They only changed the log messages when they really needed to, where previously they would change them just because they didn't like the current log message and they felt that rewording it would be a vast improvement for all of mankind. Or, number two, if they do have to change them, then they will also update our library that contains the log parsing code. And then they would check that into GitHub with the new version of their code. And we would have the updated test library, the build would pass, and when we have the new version for final testing before release, we've got updated code that runs with it. So it's very, very valuable to integrate the tests into the build pipeline and to use the same language that the developers are using. Problems and pitfalls to avoid. Never think that specification by example, or BDD, is a QA process. Seb pounded on this yesterday. It's not a QA process. Yes, it's valuable to QA. Sometimes it begins in QA, but it's all about collaboration and defining a common vocabulary. If any one group writes the requirements without everybody being involved, then you lose the value of that collaboration and you may lose the common vocabulary. If the developers aren't present and the product owner and the BA go off and write the requirements, the developers may not understand the application-specific meaning of a particular word that's used in the requirements, and then they may write the wrong thing. It's a software development methodology and a team process, so don't let one group write the requirements in isolation. Never pick an automation language that your developers aren't using. You could have more than one automation language. For example, if you write requirements and you want to test them against both a website and the API behind the website, you might have JavaScript and Cypress for the website and Python and Behave for the API, although you could use Python and call Selenium from Python to test the website. So your web developers are certainly going to be using JavaScript, and your application developers might be using Java or Python. So stick to the languages that your developers are using. Communication with them is just critical to your success. And that communication is going to be hindered if you're using different languages. Don't build tests that run for hours. They're not going to get integrated into the CI/CD pipeline if they do that. And they're going to deliver less value because they're not run as frequently. And finally, never, ever Google BDD tutorial or Gherkin tutorial. I was delivering a class once on specification by example, and I had broken the class up into groups of 4 or 5 students to collaborate on an exercise. And I was walking around listening, answering questions, looking over people's shoulders to see how they were doing. And I saw one student who had his phone out, and he had Gherkin, specification by example requirements on it. And I recognized the requirements. And I thought, why do I use these requirements? And then I realized I recognized them because I Googled BDD tutorial or Gherkin tutorial, and I used what I found in our bad Gherkin section of the class. So if you Google BDD tutorial or Gherkin tutorial, most of the tutorials you find will teach you bad practices. Specification by example is where Agile was probably 10 years ago. Lots of people were experimenting with Agile 10 years ago, and probably most of them were doing it poorly. Specification by example is the same way. You'll see a lot of bad Gherkin bad requirements if you go out there and Google Gherkin tutorial or BDD tutorial. So I'll give you some good resources. Cucumber.io, the website of Cucumber Limited, the folks who created Cucumber. Seb Rose is there. They've got a great blog section, wonderful blog posts there. Goico.net, Goico Adzik wrote the book Specification by Example. Behavior-Driven Development with Cucumber by Richard Lawrence and Paul Rayner, highly recommended. It's a very small book, very easy to read, very, very good. Has a little bit of programming in it, enough to explain how to do things, not so much that I think a business analyst or a product owner would go, I can't read this. I think that they would be able to read it very easily. You don't have to understand the program examples in order to be able to read the whole book, I think, and understand it. So highly recommended there. If you're only going to read one book, read that one. Specification by Example by Goico, very, very good, much thicker than Behavior-Driven Development with Cucumber, but very good. The Cucumber book, or the Cucumber for Java book, written by the folks at Cucumber Limited. And that is a book for developers. So it certainly explains how you do specification by example, how you write Gherkin, but it also explains in great detail how you do the automation. So all of these are trustworthy resources and recommended. Costa, what questions do we have?
Do you have any funny stories to share with us about your?
Well, certainly the one about certainly the one about the guy who was it was a smart move. Smart move. He's in a class on specification by example. He's learning Gherkin. Smart move. Pick up your phone, and they didn't bring laptops. I told them, don't bring laptops. You don't need them. We're not going to use them. You know, smart move to pick up his phone and Google Gherkin tutorial. and as soon as I saw that, I was like, Oh my gosh, this is something I must add to the class that I tell everyone right up front. Oh, don't do this. so, so it was very amusing. Um, Other good stories, the business analysts at General Motors, after they transitioned from traditional requirements to requirements written this way, about a year later, they told me that this methodology did not save them any time. If anything, it cost them a little extra time up front. But they said, once we write the requirements, there are no more questions. There are no emails, there are no Slack messages, no phone calls, no one stopping by our desk to ask us, what does this mean? And they said, we'll never go back to doing it the other way.
All right, so we do have a question that just popped in. Maria asks, how can SBE be integrated in data warehouse testing when the source data is pretty dirty?
Well, again, in a data warehouse, you typically have an ETL process because you do expect to be getting in dirty data, and and you want to clean that data before you feed it to the application. So all of the section here about ETL requirements should apply to a data warehouse. Your application either has to convert all of that data, you have to convert it in an ETL process, or the application itself has to deal with it. So you would write the same types of requirements.
I had a question for you. What inspired you to get into specification by example and go down this path?
I'm always looking for more efficient ways to do test automation. And back probably 5 years ago, I was looking for new automation tools to see what was out there, and came across Cucumber and began studying it, and realized that there was the opportunity here for real value. And so I did a proof of concept, and I tell everyone in my class, the first time you write Gherkin, you will write bad Gherkin. We all do, and I did. I wrote bad Gherkin, and I looked at it and I said, I don't think this is right. I don't know why it's not right, but I don't think it's right. And I went back and reread some chapters in specification by example and figured out why it wasn't right, and then realized once I do this the right way, the efficiency goes way up. The code reuse goes way up. The amount of code maintenance for the automation goes way down. And those things are very valuable to me. I care about that. I then talked Aslak Helisoy, the author of Cucumber, into coming to Atlanta and teaching the first class they had ever taught on this side of the Atlantic, and sat in on that class, enjoyed it very much. And I've since then just wanted to share that there's a better way to do things than writing manual test cases first, and then automating from the manual test cases, and then spending a ton of time doing maintenance. For a website we were testing at General Motors, we went from 8 people dedicated full-time to maintaining the automation code and delivering it one release behind the developers. We went to 1.5 people maintaining and updating the automation code and delivering it at the same time the developers delivered the code. That's a huge efficiency gain. Got a question there, Costa?
Yes, that's awesome. Thanks for sharing that, Leslie. So the question that Richard has was around how does Cucumber handle heavily data-driven tests? Basically, focus less on the Gherkin.
So Again, the data-driven, if you can break it down into small pieces of the data, small examples, then you can write requirements that use data tables in the given part to say, this is the data coming in. When feature generation happens, ETL happens, whatever it is that happens, then this is going to be the result. So data-driven works very naturally if you use data tables for your givens, your inputs, your preconditions. That's also why we decided not to use PyTest BDD, although PyTest is very, very commonly, widely used. I mean, it's just the de facto for unit testing in the Python world. PyTest BDD does not support data tables, and that's a huge disadvantage, and you cannot use PyTest fixtures in their place because you have then separated the data example from the business rule and the outcome.
So we had another question come in. Charles asks, this is a bit speculative, but Charles asks, is meta machine learning in our future? Meaning, for example, a machine learning farm in which a supervising machine writes requirements for farmer machines, or is this too sci-fi?
I think that it will happen. They're already using, I mean, if you look at generative adversarial networks, GANs, they're using a neural network to drive the learning of other neural networks. So yeah, I think that's going to happen.
I guess just to kind of add on to that last comment, so where do you see us heading in the next 5 to 10 years? What excites you about the possibilities of what's possible in the future of testing?
Well, certainly automation is so critical now, and data science and machine learning and AI applications are just becoming ubiquitous. I mean, they're all over the place, and it's critically important that we understand how to test those things, how to add value for the organization, for the developers. And so I think this is a very, very key skill for people who are in the QA world to look first at specification by example and learn that, because you can apply that to any type of application. And then also to look at data science and machine learning and go, do I want to jump into this? Because it's going to be a huge expanding field for as far out as I can see.
Awesome. Well, thank you so much, Leslie. Appreciate your time as always.
All righty. Enjoyed it.